Now, today, first I'll study the transformation of electromagnetic fields. So last time we said that we have a field strength tensor F, and let's say that's the antisymmetric matrix gamma delta, and under the transformation it goes to the F prime alpha beta, and the form is in the following. So let's say that this is the transformation boost matrix, and gamma is contracted, goes to beta as a free index, and other index delta is contracted, goes to the beta as a free index, and gamma is contracted, and the free index is alpha. So, and we said that you can write this equivalently in the matrix presentation as the F prime F A transpose A, and A is the boost matrix. So we can derive easily the boost matrix in 3 dimensions. Already we have the boost matrix in 1 dimension, and let's say that we have coordinates x1, x2, x3, and the other, let's say this is the K frame, and the other frame moves along the x1 direction as a K prime, is boosts along 1 direction, so let's say beta x, something like this, b x over c. So the field seen here has electric field and magnetic field, and this field seen here E prime and B prime. So how we can transform? We can transform with the help of the boost matrix. We have studied that the boost matrix in 1 dimension, we transform the time and space coordinates. We can transform the 4 potential. We can transform the 4 velocity and so on using the boost matrix. And now we will transform the field strength tensor. So the open form is the following. This is equivalent to the following. We have a field strength tensor. So the elements is 0 minus Ex minus Ey minus Ez. It's an antisymmetric tensor, Ex, Ey, Ez. So if you write cell by cell, the situation is the following. So diagonals are 0, and the off diagonals are the magnetic fields, minus Bz, By, minus Bx, and here you have the plus signs of this. Bz minus By plus Bx. So the boost matrix in 1 dimension has the following form: gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. So cell by cell, this is the structure. So, and here we have the transpose of complex conjugate of that is the itself. So you have gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. So it seems to be huge, but I can complete this calculation easily. I want to show you that clearly that if we take this transformation in the new coordinate frame, the form of the field strength tensor is the same. It's the antisymmetric tensor, and we will see that the fields are mixed to each other. So let us calculate. So let me write this again, minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. So here, if you take the product of the matrix, what you are going to do, take the first row, multiply with the first column, what you are going to obtain, this and this, and this and this, and this and that, and that, and that will be multiplied and sum. If you do this, only surviving term is minus, minus is plus, gamma beta EX. So first row and first column multiplication. Then do the same thing to the second one. First row with the second column, and what you are going to obtain. This will be multiplied this one, and this will be multiplied that one, and that will be minus gamma EX. And what about our other terms? So this will be multiplied with the other. That will be minus EY. So minus EY. And the other one will be minus EZ. So for example, first row and the fourth column will give you the minus EZ. So if you do for the second one, so this and that multiplication will be gamma EX. This and the second column multiplication will give you minus gamma beta EX. And second and that will be minus BZ. Second row, fourth column will be plus BY. And do this again. So now I will speed up a little bit. EY gamma minus gamma BY. So that will be gamma EY minus gamma beta BZ. So third row, first column, this is correct, is the sign, it is again correct. Then the other one, third row and second column will yield you what? Minus gamma beta EY plus gamma BZ. And the other two terms will be what? What will be the other two terms? 0 and 0. 0 and minus BX. So if you multiply the third one with the third will be 0. Third one with the fourth, that will be minus BX. So the last term, so it seems to be complicated, but we will come very quickly to the end. Gamma EZ, gamma beta BY minus gamma beta EZ minus gamma by bx and 0. So let us conclude this result. Fourth row times the first column, gamma Ez minus minus plus gamma beta by, and the other one minus gamma beta Ez minus gamma by, and the other one correct bx, the other one is 0. So this is the structure. So these are the elements of the 4x4 matrices. So you can do this calculation much more easy using the index notation. I am not going to do this because I want to show you that all elements of the field strength tensors and how nicely becoming as in a covariant form, the form will not be changed. So in the new frame, you have this structure, but what will be changed? Ex prime, Ey prime, Ex prime minus Bz and so on. So let us do one more multiplication and let us find the F prime. So let us multiply this to the up. So and find the elements. So first row and first column, what will be this? Gamma square beta Ex minus gamma square beta Ex. What is this? 0. So you will obtain gamma square beta Ex from this and that, and for the other you will obtain minus gamma square beta Ex, so this term is 0. And let us look at the other term, first row and second column. What you are going to obtain? Minus gamma square Ex plus gamma square Bex, gamma square beta square Ex. So that term will be minus gamma square Ex plus gamma square beta square Ex. So first and second row calculation, minus gamma square Ex plus gamma square beta square Ex. And what is this? If you take the gamma square parenthesis, you will get what? Gamma square in parenthesis, you will get what? In the minus 1 minus beta square Ex. Is it okay? Yes. Minus gamma square Ex plus gamma square beta square Ex. What is the 1 minus beta square? 1 minus beta square is 1 over gamma square. So therefore this term is cancelled out, and that is minus Ex. Basically, if we boost the frames along the x direction, x prime is equal to x. We will see. So this whole stuff is equal to Ex prime. Now let us look at the first row and third column. So that will be what? Minus gamma Ey minus minus plus gamma beta Bz. So that is equal to minus gamma Ey minus minus plus gamma beta Bz. And that term is corresponding to the what? Minus Ey prime frame. So if you write the f prime, the form of the f prime, you know the form of the f prime, 0 minus Ex prime, Ey prime, Ez prime, Ex, Ey, Ez. So diagonals are 0, and off diagonals are what? Bz prime minus by prime, bx prime, and this will be the reflection of I along the diagonal with the minus sign, minus bx prime. And what else? You will have, what else? So that should be minus bz prime, and this reflects there is a plus by prime. So therefore this element is corresponding to minus ey prime. And let us look at the first row and the fourth column, that is minus gamma Ez minus gamma beta by. This will be minus gamma Ez minus gamma beta by. Okay, this term and the last column, so minus gamma Ez minus gamma beta by, and this is corresponding to minus ey prime. So I'm not going to calculate the 16 of them because independently how many components? 6 components. But just to show you that diagonal is okay, so it's anti-symmetric, let me show you that the second and first. What is the second row and the first column? Minus gamma square minus gamma square beta square Ex plus gamma square. So the first row, second row and the first column will give you minus gamma square beta plus gamma square Ex. So minus gamma square beta square minus gamma square beta square plus gamma square. If you take the parentheses, it is in this form. And what is this? If you take the gamma square parentheses, that is equal to what? Minus 1 minus beta square Ex. Plus. They should be plus. Is this right? So let us look at this element. Minus gamma square Ex plus gamma square Bx. And if you look at this and that is minus gamma square beta square plus gamma square. Yes, plus, yes. Thank you. So basically this element is the same as this element, but the sign is opposite of this. So if you call this is minus Ex prime, this is Ex. So the anti-symmetric form is seen, and although this element will be cancelled out. So we see two pieces such that the field here is the negative of the field. It's the anti-symmetric element we can see easily. So now I'll go fast. So as you guess, if I calculate the 2 and 2, what I am going to obtain? minus gamma square beta minus plus gamma square beta, and what else? Minus gamma square beta, and this element will be the 0. So all diagonals will be the 0. So then if you continue this and that column, you will obtain gamma beta EY minus gamma BZ. So minus plus gamma beta EY, and what else? Minus gamma BZ. And add to the last column, you will obtain gamma beta EZ plus gamma BY. So let us control the last one. Minus plus gamma beta EZ, and what else? Plus gamma BY. So you will have then 0 here, and this element will be the what? This element is corresponding to the minus BZ prime. And that element, the other one next to it, will be the BY prime. And so if you continue, you will find that here, you will find that the BX prime. And what is the BX prime? What is the BX prime? So this element is the BX prime. Which element is this? Third row and fourth column multiplication will give you the BX prime. As you see that the BX prime is equal to BX. Okay, it doesn't affect it. So then you have the 0 here. So this will be reflected here as a EX prime, and that will be reflected here as a minus EY prime, that and that. And what else? Where is the BZ? BZ minus BZ prime here. It's reflected here as a positive BZ prime. And then what else you have? You have minus EZ prime, and that should be the plus EZ prime. And this would be the minus BY prime, that one. And the next to it, that would be the BX prime. So basically, we compute that the diagonals have to be 0, and we calculate that the EX, EY, and EZ prime. So this is EZ prime, and the antisymmetric part is here. So this piece is the minus BZ prime, and that is the BY prime. Now, let me write that the transformations. So I see that the minus EX prime is equal to EX because of this transformation. So let me write that the transformations here. EX prime is equal to EX. How about the EY prime? Minus EY prime is equal to minus of that stuff, multiply with minus, then write that the EY prime is gamma EY minus beta BZ. Gamma EY minus beta BZ. And how is the EZ prime? EZ prime here, minus EZ prime. So therefore EZ prime will be gamma EZ plus beta BY, this element, and BX prime doesn't affect it. Bx prime is Bx. By prime is there. By prime is gamma by plus beta Ez, if you take that gamma parenthesis. And minus Bz prime is here, so that is equal to Bz prime is equal to gamma Bz minus gamma beta Ey. So if you do this index notation carefully, maybe this is 10 minutes or 15 minutes and we spent half an hour. Okay, but we see that when we transform the field strength tensor, we are getting the same structure in the different frame. We boost along the x direction, we obtain these fields. If you want to calculate the unprimes, all you have to do, change the prime with unprime and let the beta as a minus beta. For example, By is equal to gamma By prime minus beta Ez prime. So you can do this. Now let me try to write the three-dimensional transformation of the fields using this piece of information. So if you want to write for general electric field E prime, write all E's as a x component is the same, y component is gamma Ey minus beta Bz J, and for the z component, gamma Ez plus beta By. This is the z component. Now the boost was along the x direction. So let me say beta is a beta x. And add a term with gamma EXI, subtract the same term. That is help us defining the field in 3 dimensions. So this is the Ey prime in terms of unprimes. This term is the Ez prime in terms of unprimes. Beta is beta x. So basically what you have, if you add gamma Ex and subtract the gamma Ex, you will get what? Gamma Ex, gamma Ey, gamma Ez. So E prime will be the following. E prime will be the following. In gamma parentheses, you will have Ex I Ey J plus Ez K hat. So this piece, no, that not that. This piece, and that piece is there. And then pick up the terms with the beta x. In gamma parentheses, which terms we have? So in gamma parentheses, we have, so I should use better the board. So in gamma parentheses, we have what? Minus beta x Bz. Where is this? beta x, bz, and along j. And what else we have? In gamma parentheses, beta x, by, beta x, by, this term along k hat. What is the leftover terms? I used all gammas, but I did not use this and that term, and that is equal to plus 1 minus gamma ex I. So did I close the parenthesis? This is the gamma parenthesis I should close. So let me repeat the situation. Gamma ex, gamma ey, gamma ez, all is here. And in gamma parentheses, minus beta x, bz, we have along j. And what else? In gamma parentheses, bx, beta x, by, along k hat. And the leftover terms is what? Ex minus gamma ex. So basically, what is this? This term is equal to what? Can we call this term as a I, j, and k of beta x, y and z components are 0, bx, by, and bz? Yes, I can, because if I close this one 0 and 0 and close this one, beta x, by is there. And if you close this one, I have what? Beta x, by. So for this one, I have beta x, bz. Where's the beta x, bz? Is here along j direction. If I close this one, I have what? Bx, by along k hat. So this is the piece of the cross product. So basically, this term in general could be expressed beta cross b. So this is for x component. So this is nothing but full electric field. And the only leftover term is 1 minus gamma ex. So you can write this in the following form. So let's say that this is equal to, this piece is equal to following. Let's say that is minus gamma minus 1 ex multiplied by gamma plus 1 divided by gamma plus 1. And take the minus sign a little bit here and multiply by gamma square and divide by gamma square. So this stuff says something to us. So the situation is the following. We have minus gamma minus 1 ex. So I multiply gamma minus 1, divide the same, and gamma square and gamma square. So the stuff over there will be the following. These two is gamma square minus 1, these two. And take this gamma square is here. What is left? I use this term, and it is left with minus gamma square gamma plus 1. Okay, I use these two here. I use gamma square here. What is left? Gamma plus here. Gamma square is there, and ex. So gamma square minus 1 over gamma square is beta square. Gamma square is equal to 1 over 1 minus beta square, and beta square is equal to gamma square minus 1 over gamma square. So they are the same. So instead of this, I will write beta square, okay? That part is trivial. So instead of this part, write beta square. So this component along the I direction, and for the last component we can write the following. So I will write the last component again, then I will write the full result. So instead of this, I will write minus gamma square over gamma plus 1. For we have beta square Ex, and Ex could be written as Exi could be written as beta hat x beta hat x dot E. This is the x component, and in general you can write for any direction. Okay, projection of the E along the beta. So if you distribute this beta here, that will be beta vector, and that will be the beta vector. So instead of that, you can write beta dot E. So the full result you will use in quantum mechanics, relativistic quantum mechanics, and here is the following. The electric field in the new frame is equal to in gamma E plus beta cross B, and the leftover term is minus gamma square over gamma plus 1 beta dot E. So this is the one important transformation for the electric field. So the last moments are the following. We write that the beta square there for the Ex. We write that the projection of the E along the X component of the beta, and that is a scalar and along X. So basically we said that the beta hat be the I hat. So that becomes Ex, and this is the I hat. So that is the definition over there. So basically the situation is the following. You can do the same transformation to the B, and you will obtain the B prime as gamma B minus beta cross E minus gamma square over gamma plus 1 beta dot B. So these are the fields are seen in the moving frame. So as I said, that is very easy using the index notations, but I made it difficult to see that every piece of what we are doing much more clearly. Then if you want the inverse of this, it's very easy. Prime will be unprime, that will be prime, that will be minus beta prime. Here 2 times minus minus will be, this doesn't affect, and that will be the prime. You can replace the prime to the unprime, beta to the minus beta. So inverse of this, E prime goes to E, beta goes to minus beta. So we will use this in solving questions, and also we will use this where motion in the charged particle under the electric field and magnetic field. So the next thing for this chapter we are going to study today is the fields of the moving electric charge. So the electric charge will move with constant velocity. It is not accelerating. We will study that the fields of the accelerating charge next time. So maybe a couple of weeks later. So this situation is the following. Let's say a charge is moving with velocity v along x1 prime. So let's say this is x2 prime and x3 prime is outside the blackboard. Charge is moving with constant velocity, and this is the k prime frame. So here, let's say the rest observer x1, x2, and x3 looks the field at somewhere here. Somewhere here is the B, let's say B. Along x1 and x2 plane, somewhere here, looks the fields. So with respect to the moving observer, the fields are what? Primes. With respect to the moving observer with the charge, only electric field exists because moves with the charge with respect to the here. But with respect to the rest observer, you can have the mixture of the fields. You can also observe at the mixture of the fields. So basically, the situation is the following. This k prime frame moves with omega t, and with respect to the k prime, the coordinates are the following: ct prime and x prime in 3 dimensions. And with respect to the rest observer, we have ct and x. So with respect to the moving observer, the length from here to point of interest is r prime, and time is t prime, so therefore this point is minus vt prime with respect to the moving observer. So x component will be the vt prime. B component doesn't affect it because that is perpendicular to the motion. So with respect to the k prime observer, the situation is the following. x1 prime, x component, is minus vt prime. x2 prime is b, and x3 prime is 0, and time is gamma t minus v over c square x1. But x1 is 0, so that is 0. So the coordinates seen in the moving observer is this. So the electric field seen from the moving observer is the following. So at this point it has one electric field here, and let's say that this angle is theta prime. So this electric field has a projection along what? x1 minus x1 and x2, not the projection on x3. So the components are the following. E1 prime with respect to the k prime observer, x component of the electric field will be what? Minus q over r prime square. R prime is this length, and cosine theta prime. Because this is theta prime. And E2 prime will be what? Q over r prime square sine theta prime. So these are the components of the electric field seen from the moving observer. So let me erase this part and continue until we finish this part, maybe 20 minutes more. Then we can give a break and start a new chapter. So r prime is equal to b square plus vt prime square, and t prime is gamma t. So let me write again E1 prime, that is equal to what? So let me write one more thing here. Cosine theta prime. What is the cosine theta prime? Cosine theta prime is equivalent to what? Cosine theta prime is what? Cosine theta prime? Vt prime over r prime is the cosine theta prime. So that is equal to what? Minus q r prime square. Cosine theta prime is vt prime over r prime, and t prime is gamma t, and we can obtain what? E prime, x component of the field seen in the moving frame, will be minus q gamma vt, because t prime is gamma t, divided by r prime cube, and r prime is b square plus gamma vt square, because t prime is gamma t. So that is equal to b square plus gamma square v square t square 3 over 2. So this is the x component of the field moving seen from the moving frame. For the y component, instead of sine theta prime, you can write what? B over r prime. So that will be the following. E2 prime will be what? Q over r prime square. Instead of sine theta prime, I can write b over r prime, and that becomes q b over r prime cube. Therefore, E2 prime takes the form of what? QB over r prime cube. R prime cube is again the same. B square plus gamma square v square t square 3/2. So these are the fields seen on the point B with respect to the moving observer. So what are the other fields? Z component of the electric field is 0 because this is the plane we are looking at the field at the x1 and x2 plane. So basically E Z prime is 0, and with respect to the moving observer there is no any magnetic field. Bx, By and Bz are all 0. So these are the fields are seen in the K prime with the moving observer. Now what we need to calculate, fields seen at the rest observer K. So what we are going to do, we will use these Lorentz transformation tools. We have primes here. What we needed, we need unprimes. So unprimes are the following. So if the motion in one dimension along the x, we have seen that the x component doesn't affect it. So therefore Ex is equal to Ex prime, and no, let me say E1. E1 is equal to E1 prime, and that is equal to minus Q gamma Vt over B square plus gamma square V square T square 3/2. This is the x component. So let me use as a x. So 1 is x. How about Ey prime, Ey. So Ey is equal to what? Ey is equal to gamma Ey prime plus beta Bz prime. So you make this unprime, prime, prime, and with the negative side of beta. So beta z prime is 0. So what is the Ey prime? Ey prime is this. Okay, Ey prime is the E2 is the Ey prime. So that is Ey. This is y. So therefore Ey will be gamma times QB divided by B square gamma square V square T square 3/2. So this is the Ey component. This is the Ex component. So you are seeing that the one thing, actually what is Vt? What is Vt? With respect to the here, what is this Vt? Vt is the distance between the two frames. When the distance is minus infinity, field is what? This goes to minus infinity, field is 0. So when Vt is 0, means that the frame is here and the point here there. So, okay? So when you put Vt is 0, you will see what? the vertical component of the field, gamma QB over what? When you put here 0, that will be what? B cubed. So not a B cubed, yes, a B cubed. So one of the B's will be cancelled. That will be B square. If it is non-relativistic, that will be gamma will be 1. That will be Q over B square. The ordinary field we will see. But you are seeing that the vertical component is amplified by a factor of gamma. I will draw this. So the fields is not symmetric with respect to the rest observer if the charge is moving. The fields are symmetric, spherical symmetric with respect to the moving observer with the charge. So let us complete the discussion and continue. What else we have? We need to calculate the other components. So what is EZ? EZ is equal to gamma EZ prime minus beta BY prime. Again, we make this unprime, prime with the negative sign. What is EZ prime? Is 0. What is BY prime? 0. Therefore, EZ is 0. So this is XY plane. So on XY plane, we don't expect the EZ. So how about the BX? BX is equal to BX prime. And BX prime is 0. No magnetic field along the X direction. X is this direction. And how about the BY? BY is gamma BY prime minus beta EZ prime. So make this again unprime, prime with minus sign. And what is BY prime is 0. What is EZ prime is 0. Therefore, this is 0. No BY. Okay. Now the crucial point now, BZ. BZ. BZ is equal to gamma BZ prime plus beta EY prime. So BZ prime, unprime, prime with the negative sign. BZ prime is 0. But how about the EY prime? EY prime is here. EY prime here. So therefore, we obtain gamma no, here's the yes, we obtain what? Gamma beta EY prime. And that is equal to, if you put the value, what is this? Gamma beta EY prime, that is beta gamma QB beta square gamma square V square T square 3 over 2. So what we are seeing that we have a magnetic field along the Z direction. Z direction is the outside the blackboard. So we studied that the fields of the moving charge particle with constant velocity. We observed from the rest frame K, and the point of interest was along the what? X and Y plane. We see that some deformation in the electric fields, and I will discuss this, but we see that some field BZ outside the blackboard. So basically the situation is the following. The moving charge is creating a field. Actually, if you continue this field is something like this. So here outside the blackboard, if you calculate the opposite, that you will find that the field is inside. So with the right-hand rule, you can determine the direction of the field. So that B field is generated due to the motion of the charged particle if we observe in the lab frame, and that is the property of the transformation of the Lorentz transformation of the what field Maxwell field strength tensor. Now and what else we can study? We can study that the form of the fields. So the field seen in the rest frame EY. Okay, I was looking at this formula. So if you look at this, okay. So EY is gamma B over divided this bunch, and this bunch is here. So this is nothing but EY. So basically the created magnetic field is beta times EY. So this piece. So let us plot this and see what is going on well. So the practical situation is the following. If the charge is moving with some velocity v, it will generate a magnetic field. That field is lower if you move away from the source, and you can determine the direction of the field, B fields, with the right-hand rule. So if it is in the same axis, the field is amplified, but if it is moving away, it will decrease. So why? Because B field is related with what? Beta times EY, and EY is maximum when Vt is 0. Means that our point of interest and the moving charge in this same x, okay, same frame. So if you plot the EY as a function of x, the situation is the following. EY as a function of x means that the Vt, when Vt is infinity, so y component is 0, and y component is the maximum when Vt is equal to 0, and the value of this is equal to gamma q b square, and then so the value is maximum. So if this charge is at the minus infinity, no field here, and when charge comes there and passes just under the point of interest, that is Vt is equal to 0 at this point, then the field is maximum in vertical direction. The value is gamma qb square, and when the charge moves away, again the field will be die. If it is moving non-relativistically, gamma is close to 1, the situation is something like this. So when gamma equal to 1, that is QB square. Something like this. But the area is the same. If you calculate the impulse multiplied with the charge and take the area, it doesn't change. So the area of this and the dashed line will be the same. That is the impulse if you multiply with the Q and integrate. Q is the charge. So basically, with respect to the frame of charge, the fields are symmetric everywhere, all electric fields. But if the charge is moving some high speed, the fields are amplified along the vertical direction, perpendicular direction. These are the electric fields. It is not spherically symmetric and more in the perpendicular direction. And at the same time, it carries a magnetic field and with respect to the rest observer. And the value of the magnetic field is beta times EY. So basically, it will have some magnetic field. I cannot plot this well, so B here, and that B will be less and less if we are looking at the B farther distance from the source. So basically, if the charge is moving, the fields are, with respect to you, observer, the fields are perpendicularly with higher electric fields, and you will see that some magnetic field, the magnetic field, if I have a charge, the magnetic field is less when the charge is away from you, but the value will be increase and increase at maximum when it passes nearby you at the closest distance, then the value will be decrease again. And you can determine that the direction of the field with the right hand rule also. So here is the B is outside and here the B is inside. Now, this is important for the calculation of the high energy particles when they enters the medium. They calculate that the ionization losses, and they use this formula. They calculate the impulse. Impulse is the force integrated with the time, and multiply this by charge and integrated this area will give you the total impulse seen by the other charges if there are more charges in the medium. And we will see this, we will use this if we can come, and I will try to come when we study the cyclotron emission and the Bremsstraße emissions. We will need these fields because the charges are moving relativistically. Okay, now we can stop and we are ready to start the new chapter.